Okay. I think we should get back to P-Chemy stuff. It's been a while. What did we talk about before we had the Quizlet?
There's a whole bunch of wave functions.
Yep. So let's even take a step back from those wave functions and equations. What type of system were we looking at?
It's like a particle in a box that has a barrier.
Yep. So particle in a box, but with a finite barrier, right? So then we said we technically had 4 regions, but we ditched those regions, right? What regions did we have? Yeah, region 1, region 2, region 3. And then Lily, you said we came up with wave functions for each of those regions, right? Psi of region 1, I'm going to call it. That was a e to the ik x plus b e to the negative ikx. Okay. Region 2, I botched, but it was, we picked m and n, right? E to the k prime x plus n e to the negative k prime x. In region 3, we distilled down, right? So instead of looking exactly like region 1, where the particle can go back and forth, what did it look like? Yep. So we had c e to the ikx. And then we defined these k's because they were just a collection of constants. Let's see. K was 2me over h bar squared, right? And then k prime, which was actually one of the questions on your Quizlet that I think everybody skipped for the most part, but I can't remember, was almost the same thing, except we pulled out the potential, because the potential in this case was just a constant value, right? Okay. Then we arrived at a point where we took derivatives of things, we looked at bounds, and we ended up with 4 equations. Do you guys remember what those equations were? Or do you have them written down somewhere? And they really had to do with just those coefficients out front. First one was a plus b was equal to what? Yep. And we got that one by just setting the bound of x is equal to 0, right? So what bound did we use to get that? Yeah, so we're talking right around that edge, right? But we also had to take a derivative to show continuity, and we also ended up with this as an expression, I believe. Is that right? Or did we not do that? We did it? Okay. Then we had to look at our other bound at L, right? That one was a little bit different. K prime x e to the I. Oh, except it wasn't x. What was it? Oh, do we have x? Should be L. That's in there. L is equal to C, E, and then K prime, M, E, K prime, L, minus K prime, N, E, negative K prime, L is equal to I, K, C, all of that junk. Okay. Now, what we would need to do is solve for these coefficients. We could do that. It's tedious. I really don't want to show all the mathematics. All you have to do is just keep subbing equations into one another, and you can solve for it. What I do want to figure out is if we have a particle along here, how much of it gets transmitted across? So depending on this barrier, how many of the particles will make it through that barrier? So what I want to do is get an expression for transmission. So we're going to take T. We want to consider the total number of particles traveling this way. What region is going to get us the initial amount? Yep. And the one's traveling this way, so what do we want to be concerned with? Yeah, A. So we're going to look at A. And since it's a probability, what do we? Yep. And then those that make it through, what coefficient do we want to care about there? Yep, C. We want to take the absolute value and square it, and that will get our probability of transmission. Okay, let's find an expression for that. Like I said, if you're really bored or have a lot of time, there's like 4 pages of just scrambling notes that get you to this. Are you okay with just jumping to the punchline? Am I okay to erase this side? Okay, you sub all those equations that I'm erasing into one another, and you make a substitution. And what you end up getting is the following expression. Where epsilon is equal to this. Sorry, I'll write that E a little better. Okay, we can modify this even further. If you have a very high, meaning the potential is really big, and wide barrier, you can simplify this expression. For high and wide barriers, What we mean by that is if a or k prime x is much larger than 1, what would happen to e negative k x if this value is really, really big? So that's really, really big. It's a negative exponent. What could you approximate its value to be? So we can say it's approximately equal to 0. What do I want to do here? You can transform this guy. Into e 2k prime to that. Okay, if you want to have this expressed in a different way, I don't like things raised to the -1. Get 16 epsilon 1 minus epsilon e to the -2k prime x. Okay, so sometimes we'll have to use this one if we don't have a very high and wide barrier. We'll talk about what is a high and wide barrier. Otherwise, we can utilize this. Way easier to look at it. Okay, the next thing I want to ask you guys is what does this wave function look like then? So let's say the wave function in this region is meant to look like a free particle. It's going to look like this. What happens to the wave function as it's in the barrier? Which way does it want to be pushed? So let's do it this way. I'm a quantum particle. I walk into the wall. What way is the wall pushing me? Yeah, backwards. I don't go really into the wall too much. But in this case, it does. So what happens to that wave function? What's it going to look like as it gets pushed back this way? It'll look kind of like this. Like a dying exponential. It's getting pushed back that way. And then what does it look like on the other side? Yeah, smaller. The amplitude isn't as much. And which way is that particle traveling then? Yeah, it's going forward in this case. Okay. Now, this is pretty strange when you consider classical physics. In classical physics, I can throw a ball at that wall, and what will happen to the ball? Yeah, it'll come back depending on how hard I throw it. If it's a rubber ball, it'll bounce all around. I'll miss it because I'm horrible at catching things. But in this quantum world, if I shoot an electron at that wall, what will happen most of the time? It'll bounce back. But what can happen every once in a while? Yeah. So this is strange because that doesn't happen classically. Oops. So that means if you have any sort of finite potential, a quantum particle can just hop through it sometimes. And it happens. You've seen it in organic chemistry when there's like a proton that just shuffles or a methyl. In terms of devices like processors, this is actually the reason why we're running into a problem with how small our processors are getting, because the potential difference isn't big enough so things can hop through. It happens with DNA, which is cool. And I'm going to show you a video in a second where they've actually utilized this to visualize atoms, which is cool. So the particle can tunnel out of a potential. This is really strange because classically this can't happen. Okay, how many of you have actually ever seen an atom? Probably not, right? They're really small. Have you ever heard of something called a scanning tunneling microscope, or an STM? What was that? Maybe. I know I've pestered, I think, you two about it at one point, but you probably have never seen one. They're a really expensive instrument where you can actually visualize molecules on top of surfaces. You can look at their electron density. And the way that they work is through tunneling. So this was actually one of the first ways that people saw atoms. And what I think, it was kind of in the 70s when these things were being developed, which is crazy to think about, like, in like my older brother's lifetime is when they first started visualizing atoms. So we're going to watch kind of a lame but interesting video, I think, about the world's smallest movie. And this was something that it was a stop motion animation that was developed by IBM, where they moved individual atoms on top of a surface and made a video. The really cool thing, too, I'll pause it at one point. So what we're visualizing here is actually the electron density. And each one of those little dots is an atom. Okay. I think you get the point. We don't need to see it dance around a ton. The other really cool thing to see here is do you see these ripples? It's legitimately waves because that's how the electrons are acting. So we can visualize, these are known as Fourier patterns, but they disrupt the electron density on the surface. So we can visualize that, we can see that. The other crazy thing is if you look, okay, you put an atom on this surface, you're messing with the electron density over here. So they've shown if you put a corral of atoms around, you can make different molecules bind selectively on a surface by controlling that electron density. Really weird thing, because like the distance between these two atoms is huge, but they still see each other. Okay. I know I'm really excited about this. Let's try to make you guys excited about it. So what we're going to do next is some mathematics associated with trying to figure out the probability of tunneling in more chemical systems that are more relatable, and then we'll look at it in terms of processors. Okay. So let's look at a system where we just have an acid and a hydrogen's confined to an acid. So a proton, acidic, hydrogen is confined to an acid. This acid can be represented as a potential barrier a height of 2.000 electron volts and a length of 100 picometers. Determine the probability of transmission. Probability. For the proton to escape the acid if the proton has an energy (1.995 electron volts). So we're considering this proton on some acid just going bloop and transferring across the barrier. In this case, do you guys get what we mean by a potential barrier when it comes to this molecule or this acid? Or not really? Okay. When we look at this, what's keeping this proton adhered to this acid? So why would that bond exist? Yeah, they're sharing electrons. That's always like the basic argument, right? What other type? Okay, let's say, I don't know, did Dr. Ogawa talk about like different representations of, let's say we have something like this. In inorganic yet or no? Yeah, so there's ionic interactions, there's covalent interactions, there's a bunch of intermolecular attraction forces that are happening. All of those forces of this trying to pull that proton closer to it, that's what we mean by a potential. So it's like adding everything together, all those attractive forces. Okay, let's try to calculate what's the probability of this proton just going bloop and popping off somewhere else. Okay, the first thing that we need to do is we got to figure out an expression for what we want to use. Let's start with our unmodified expression. Ugh, gross. Okay, what are some things that we need? At least in this expression. Yep. So we need epsilon. Energy divided by potential, right? That's easy enough. What's our energy in this case? Yep. Yep, and what's my unit? Yep. And what am I dividing by? So what's V again? Yep, the potential. What was that? Yep, just this potential. We're going to use that. So what value? Yep. Okay. When I do this math through, do I have to convert these units to anything fancy? Okay, Will's shaking his head no. Why no, Will? Yeah, they're going to cancel out. So it's really just a ratio. That ends up being 9975. Okay. Ellen, you said we had to do one more thing. I think you said find K prime. Did you say that or no? Okay, well, we got to find K prime then. Okay. What was it? 2mv minus e? Is that right? Okay, and what are we dividing by? Yep. Okay. 2m. What is our m in this case? Mass of a proton, yep. 6.7 times 10 to the minus 27 kilograms. Okay, and then we have V minus E. What will the value of that be? Yeah. Yep, and what's my unit? Mm-hmm. Okay, what do I have to do to that? Yep, what would you convert it to get to an SI unit of energy? Excuse me. Yep, it's 1.602 times 10 to the negative 19. And then we got to divide by h bar squared by 5 times joules times seconds. And everything's said and done there, we get that. Positive 10. Yep. Okay, what now? Yeah, we could plug and chug, no problem. Could we use the simpler equation though? So we wrote another equation, a simplified one, which I'm going to write in blue. Like that, right? Can we do it? Can we use that one? What would we need to check? Yeah. So you'd have to check if k prime times x is greater than 1. Okay, let's check that. K prime times x, or k prime we have is this value. What's our x in this case? Yep, the length. The length of the potential, right? And what was the length of our potential? Yep. How do we convert picometer into meter? Yeah, 10 to the 12th picometers for every 1 meter. We multiply that through, I get 1.550. Is that right? Yeah, should be. Okay. What's my unit on this number? Nothing. Yep. Okay. To use this equation, what do we need? Yeah, must be much greater than 1. Isn't much greater than 1. No, shit. We have to use this one. Okay. All right, we can do that though. We can just plug in all of that stuff, right? We have literally found that and that and those things. The rest is just doing manipulation. Okay, so when you calculate everything out, that is the result. Okay, what does that mean? Yep, so what would be the likelihood or the percentage? To tunnel. Does that seem like a very big percentage? It doesn't. But how many particles are we talking about here? Yeah, like if you have a mole of water molecules, it really isn't that much water, right? Like 1 drop of water, do you remember what its concentration is? Like if you had pure water, what molarity it was? About 55. Okay, so we're talking about a lot of particles. So even though this is a really small number, It's still a rapidly occurring event just because of how many particles we actually have. Okay? So yeah, a lot of times it won't happen, but every once in a while it goes blip. Then if you think about a reaction coordinate diagram, where let's say you have a barrier like that. Yeah, it might be stuck in here, but every once in a while it could just go bloop and jump right across, not even have to worry about that barrier. And if it keeps happening over and over and over again, you'll push it that way. Okay. Do you guys want to look at another example where this percentage is higher, or do you feel confident that you can do this sort of stuff, / is no one really interested?
How do we know what counts as much greater than 1?
Okay. So what counts as much greater than 1 is a value sort of similar to like you would use for equilibrium constants. So I don't know, let's say 1 times 10 to the 4th. Okay. It's better if you utilize this, but in another example that I have, what did I say? Geez, my stomach is rumbling like crazy. I'm really hungry, apparently. Let's see. If you change this number even slightly, it can modify it greatly. Okay. I know that wasn't the most like concrete or set answer, but yeah. Any other questions? Okay. Again, this is something weird and strange that has been predicted by quantum mechanics. It happens. We build devices around it. We're running into issues with our devices from this. And this is something that classically would never happen. So another example of where quantum has predicted some weird stuff and it shows up. Are there any questions about that? Your daily problem has to deal with, I think, DNA base pairs and shuffling protons between those DNA base pairs. So big thing here, just make sure your units work out. Know when and when you cannot utilize this equation. Okay? Am I all set to erase this?